Good evening, and welcome to the course on Fundamentals of Additive Manufacturing Technologies. It is 6 p.m., but participants are yet to join. So we will wait for a few more minutes before we get started. Thank you. Please allow me a minute. So, good evening and welcome to week two of the live sessions for the course on fundamentals of additive manufacturing technologies. This course is taught by Professor Sajin Kapil, who is a member of the faculty in the Department of Mechanical Engineering at IIT Guwahati. And I am Sourav Goswami. I'm a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. We were introduced to additive manufacturing and concepts like tessellation and STL files in the previous week. And there were just a couple of questions left over. We'll touch upon them before moving on to the contents for this week. The first question today deals with unit vectors of facets. And the question says that few lines of a triangle from the code of an ASCII format of a STL file are given. They are here. We have the outer loop, then the vertices, and then the end loop. And we are asked to find out the unit vector in the direction of the facet normal of this triangle. So the derivation and the formulae for this question are already covered by Professor Kapil in great detail. I'll apply them directly. Um, so say let us just assume that in the given order, the three vertices are A, B, and C. And I'll just draw a representative triangle here. And we are asked to find the facet normal. And we know that, say, if we have vectors AB and BC, then or AB and AC, then we can take out their cross product. The cross product will be normal to this plane. And if we divide it by the magnitude or the norm of AB cross AC, what we'll end up with is a unit vector. So let us do just that. First, we must find the vector AB. The vector AB is nothing but the uh, coordinates of B minus the coordinates of A, or the position vector of B minus the position vector of A. This will give us 1 minus 1 0, 4 minus 2 2, 2 minus 0 2. And for those of you who are unfamiliar, this is just another notation of writing the vector component. So this is basically equivalent to 0 I hat plus 2 j hat plus 2 k hat. Similarly, we can find the other vector AC, which is simply the difference in the position vectors of C and A. So C here is minus 4 to minus 2, minus 1 to 0, which is minus 5, 0, and minus 2. And then we do the cross product AB cross AC, and we are all familiar with how to get about this. So it's I hat, j hat, k hat, 0 to 2, minus 5, 0, minus 2, and then we expand this determinant. This is 2 into minus 2, which is minus 4, minus 0 into 2, which is 0, minus j hat into 0 into minus 2, which is 0, minus 5 into 2, so plus 10, and plus k hat, 0 into 0 is 0, minus 5 into 2 is minus 10, so plus 10 again. And we have minus 4 I hat minus 10 j hat plus 10 k hat. This is a vector in normal to the triangle or the triangular facet, but it's not a unit vector. To obtain a unit vector, we find the norm of this vector, which is simply the under root of sum of squares of these components. So minus 4 square plus minus 10 square plus 10 square. And this is 16 plus 100 plus 100. So under root 216. Thus the unit vector that we are looking for is simply uh, AB cross AC by norm of AB cross AC, which is minus 4 I hat minus 10 J hat plus 10 K hat by under root 216. Now you can simplify this further, but this is essentially the result we're looking for. Another question dealing with file formats in AM, and this asks us what pieces of information are not contained in an STL file. We know that STL file or the standard tessellation language files does not contain any information about the color of the material or the texture or the actual material composition or even the topology, because these are some of the drawbacks or limitations of the STL file format that we discussed. So all of these are true. And there are these upcoming more sophisticated formats such as OBJ and AMF. The OBJ file format encodes the surface geometry of a 3D model and can store information related to the color and texture. And this can be done either with a companion PNG file or a texture map or a material template library. Another file format called the additive manufacturing format is an XML based format for communicating the AM data, including description of the 3D surface geometry along with color, materials, lattice, texture, and constellations. It is similar to STL in the sense that the surface geometry is still represented by triangular meshes, and we discussed the reasons for choosing a triangle as the shape. But here, these triangles can also be curved and thus can provide a better approximation of curved surfaces. And we'll do just one more question before moving on to the contents for this week. This is related to deviation tolerance. And the question we are asked is, how many triangles will be required for a deviation tolerance to be 0.01 mm to represent a circle of 10 mm radius by STL format? So originally we are given, say, a circle, and it has a radius of 10 mm, and when we tessellate it, say we'll break it up into many triangles, and if I show a very coarse representation, it may be similar to something like this. Okay, all the triangles are not even here, but you get the basic idea. And the thing to note is that there is a difference in the height of the circle and the triangle which approximates it. And this difference is called the deviation tolerance. Here we have it specified as, say we denote it by D, and this is equal to 0.01 mm. And the derivation for this was already done in the lectures. We'll not go over that again. But essentially what we have is if we are trying to approximate the circle by say n triangles, and all of them are identical by the way, then the entire angle contained within the circle, 2 pi radians, is divided between n triangles, or if you are working with degrees, then 360 degrees is contained in these n triangles. And the formula which we are supposed to use is basically r minus r cos pi by n is equal to the deviation tolerance d. Why pi by n instead of 2 pi by n? That is because what we are looking at is half of this angle contained by the triangle. We already have the value for the radius, which is 10 mm in this case, so they can get working. In fact, r can also be taken out common from here, so this is 1 minus cos pi by n equal to d. Let us plug in the numbers. So we have 10 into 1 minus cos pi by n equal to 0.01 all in mm, or 1 minus cos of pi by n is equal to 0.99. Oh no, is equal to 0.0001 001, and cos pi by n is equal to 1 minus 0.001, which is 0.999. This will give us a value for n. So okay, we do not have space on the next page. Pi by n is equal to cos inverse of 0.999, and from here we can find the value for n. There were a couple of more questions, but we may not have the time for that. So let us now move on to the contents for this week. So in the present week, Professor Kapil discussed the manipulation of STL files, and some of the major contents covered were related to the orientation of the STL files and how we can manipulate them in terms of rotations and translations. What are support structures? How can we predict where support structures might be needed? What are the different types of support structures available? And which are the zones where we can intelligently guess for the support of for the need of these structures. Then we discuss optimal part orientation. That is, we in the last week we discussed that there may be strategies whereby we can orient the part at the beginning of build such that some objective is fulfilled, such as the number of or the volume of support structures is minimized, or supports are eliminated altogether, or we can minimize the time or the cost or have the best surface quality. Now, first about rotation. So here we have the description of rotation in the YZ plane, and x-axis is coming out of the plane here. And this point initially in blue moves to the other position, which is indicated by the red circle. And here essentially what we are doing is we are having just a pure rotation about the x-axis. And in such a case, we'll see if the original coordinates of the point were, say, y1 and z1, and the new coordinates are y2 and z2, then they can be related as follows. Given that L is the length or the position vector from the origin to this blue point, and that remains unchanged, as is the case for a pure rotation, z2 will equal L of sine theta plus alpha, alpha being the original angle subtended or angular position of the blue point from the y-axis, and alpha being the additional counterclockwise rotation that we theta being the additional counterclockwise rotation that we have imparted to it. Z2 equals L sine of theta plus alpha, and we expand that further to obtain Z2 is equal to Y1 sine theta plus Z1 cos theta. Similarly, for the Y coordinate, Y2 will equal L of L times cos theta plus alpha, and upon expansion it becomes Y2 equals Y1 cos theta minus Z1 sin theta. Since this was a pure rotation about the x-axis in the YZ plane, the x-coordinate remains unchanged, as in we are at the same height along the x-axis, and so x2 is simply equal to x1. When we put these three equations together and try to write them in matrix form, what we end up with is the new coordinates x2, y2, z2 equals some matrix times the original coordinates x1, y1, z1. And this rotation matrix given here as 1, 0, 0, 0 cos theta minus sin theta, and 0 sin theta cos theta is referred to as the rotation matrix. I think the notation used in classes are theta x. Theta being the angle of rotation and x being the axis about which this rotation is performed. Now this was the case for rotation about the x-axis, but what we can see is the case for the say xy plane where we have a rotation about the z-axis, or the xz plane where we have just a rotation about the y-axis will not be very different, and the respective rotation matrices are already computed and available here for our ready usage. R theta x, as we discussed, is simply 1, 0, 0, 0 cos theta x sin theta x, and 0 minus sin theta x cos theta x, reading column wise. R theta y is cos theta y 0 sin theta y 0, 1, 0 minus sin theta y 0 cos theta y, and R theta z is cos theta z minus sin theta z 0 sin theta z cos theta z 0 and 0, 0, 1. Now, the important thing to remember about rotations is that here we are already seeing that rotation is represented as a matrix multiplication. So, say if your point P undergoes first rotation about r theta about the x-axis, then about y-axis, and then about z-axis. You started with a point P, multiplied it with r theta x, then r theta y, right? R theta z to obtain the new point P prime. The order of this multiplication is important. From the mathematical point of view, we can see that this is because matrix multiplication is not always commutative. That is, A times B need not be equal to B times A. In general, it will not be equal. There might be some special cases when it is, but generally, AB will not equal BA generally. And so the order matters. Secondly, from say a vector mechanics point of view, we are already familiar with the fact that finite rotations are not a vector operation. That is, the order will matter. If I rotate an object first about x, then y, then z, and I repeat the same operation, keeping the values of those rotations same by changing the order. Say now first I rotated about the z-axis, then about the x and the y-axis. The final orientation will not be the same in both of these cases. Say as another example, if now I first rotate this about the y-axis, then about the x-axis, and finally about the z-axis, my new point in this case will be some uh, product of the initial vectors or initial points. So first now I'll multiply by r theta y, then r theta x, and r theta z. So it is important to keep uh, the order in mind. This is again summarized here that the coordinates of the rotated point can be given as the rotation vector times the initial point. And this is just about a point, but what about an entire facet or a triangle? To rotate a triangle, we simply rotate the 3 points, then link them up together, and you end up with your rotated facet. Thus, this operation is repeated for all the 3 points. The normal of the triangle can again be rotated in a similar fashion, where similar to a point, the new components of the unit
Hello,
normal
sir.
vector.
Hello, sir.
Uh,
Sir,
yes, hi.
actually, I have a doubt. I have a doubt, sir. Actually, I attend a class on yesterday, and the content is same. Then, sir, we can leave the class. I can leave the class or not.
No, it's totally up to you. There is no compulsion to attend this.
Okay, okay, sir.
Yeah, we'll just continue. Yeah, the rotated normal vector can be obtained in a similar fashion by simply multiplying the components of the normal vector with the rotation matrices. What is the case for translation? As you know, pure translation is one where the point is simply moved parallel to itself along straight lines or along smooth curves without giving it in rotation. Thus, the new coordinates of the point can simply be obtained by adding the displacement along the x, y, and z directions to the original, uh, say, point. And the normal vector will not change because we are not imparting any rotation. Thus, the components of the unit normal will remain the same. We already talked about support structures in the last week, but let us dig a little bit deeper. So support structures are mainly required while creating overhanging features. Again, overhanging features are those which are not supported by the structure in itself. If we try to visualize how we would have printed this T and say starting from a substrate, we deposit these layer by layer, the column, and then suddenly we have to support or we have to print this large lateral structure of T. When I try to print this or deposit this, say by some method like an FDM, where will this material go? It will simply fall down. Only the center will be supported, but the other material will fall and reach the substrate. Then how do we print this structure? We do it with supports. That is, in each of the previous layers, along with printing the part which I am indicating by blue here, we have also printed these tiny supports. And as we discussed, the supports are typically weaker than the actual build material. They may also be built from a different material which is more susceptible to, say, chemical attack or can be broken off more easily. In the case of FDM, it is often broken off just with your hands or, say, with a plier. And so in each layer, we are printing the support structures. Now that you have the support structures in place, you can actually print the large overhanging features. Of course, this is just a gross simplification, but you get the principle. Now, in some AM processes, such explicit support structures may not be required. And two such processes are binder jetting, where, as we remember, we have a container or a vat full of powder, and we are selectively dispensing the binder droplets in the regions which you want to harden up. And powder bed fusion, where again you have a bed on which a fine layer of powder is spread, and you selectively sinter or melt regions of interest by, say, a laser, and then you move the table and a new layer of powder is spread. In this case, the loose powder which is available in the vicinity of the printed structure itself can act as the support material. However, in some of the other processes, such as FDM as we discussed, or DED, or laminated object manufacturing, such support structures may be needed during the pre-processing stage itself. It is a sacrificial material, that is, once we have printed, we will have to remove and get rid of the support structure. They are not really useful in the end application. And the need for support structure can be ascertained from these triangular facets and specifically from the normal vector of each triangular facet. If the build direction is vertical, which is usually the case along the positive z direction, then the triangles which are having normals pointed upwards will not require any support structures. And the normal whose no, facets with normals pointing downwards may require the support structure. It might sound like a lot, but it's very easy to understand. Say you have something like a pyramid, and we are just zooming into this region. So here locally, this is what my surface will look like, and I will approximate it by say some triangle or something. Mostly the triangle will be in the plane only. It will be flat, and clearly you can see that the normal to this surface will have a direction like this. It is making a positive angle with the horizontal, or it is simply pointing upwards. Whereas if we now invert the configuration, look at a region such as this. This is my triangular facet, and this is its normal vector, and it is pointing down. When I say down, it is having a uh, angle below the horizontal. So in the first case, we can clearly say that supports are not required because the normal facet normal is pointing upwards. In the second case, it may be required. Why may? Because if even if this angle is below the horizontal by a small extent, this immediately need not imply that a support will be needed. Only when this angle is very large or above a certain critical angle that support structures may be needed. And the criticality condition is also derived here. So on the right hand side, we have a staircase-like feature of layer thickness T, and because of this, the overhang which will be generated is small d. We see that here the feature which is being tried to be represented has a downwards facing normal vector which forms an angle theta with the build direction or the vertical z direction. Important to know that this theta is with the build direction. Then the critical angle is obtained by pi minus tan inverse of t by d, t again being the layer thickness and d being the length of the overhanging feature. And for all angles that this facet normal makes, which are less than theta, support structure will not be needed. What is a simple and efficient way to quantify this angle? It's simply the cos inverse of the z component of the facet normal. We also have an illustrative example here. We'll just go over it quickly. So in an AM process, the maximum possible layer overhang can be 1 mm. This is small d. The build direction is plus z as usual. The minimum possible layer thickness is root 3 mm. This is equal to T. Find out the critical value of the Z component of the facet normal of the triangles of an STL file beyond which the support will be needed. So first, we find the critical angle theta, the formula for which is already available here. A is root 3 mm, D is 1 mm. We find that the critical angle is 120 degrees. Now, all facet normals which have uh, angle greater than 120 degree with the build direction will need supports. Cos inverse of the z component of such facet normals is equal to 120 degrees in the limiting case, and thus the value of the z component of these facet normals comes out to be equal to minus zero point 0.5. For all vectors or all facet normals which have a z component more negative than zero point 0.5 or numerically less than minus zero point 0.5, they will be requiring supports. And we can also make intelligent guesses, such as the bottom surface here, highlighted in yellow, will require supports because that entire, you know, projected area is unsupported, but also the bottom surface of the build itself. And the reason for that is actually pretty simple. So typically you will be building on a substrate plate or a build plate, and whatever your geometry, often in processes like powder bed fusion or FDM, we would need to remove it from the build plate, and we would just have some weak supports here, which can give you the necessary machining allowance, as well as can preserve the geometry of your part and can prevent damage to the build plate itself. In other processes such as DED, typically we may not use support structures at the bottom, and the understanding is that we'll separate it directly from the substrate plate and may have some allowance for it in the design itself. The next topic is support generation from the facets. And here we have the general case. Here is the triangular facets that we typically encounter in STL files. And here the build direction is already assumed to be positive Z. If the case is more generic, we'll refer back to the derivation here. But for the usual case, which is the support direction, the build direction being aligned with positive Z, we can directly end up with the equation which allows for calculation of support generation given here. And we'll also use it in some illustrative examples. The idea here is that we are simply projecting any uh, three-dimensional, not three-dimensional, any triangular facet in 3D space onto the XY plane. And because of this projection, the X and Y coordinates of each of the points will remain the same. Only the Z coordinate becomes 0 because now we are on the XY plane. Similarly, the volume of the support structure can also be obtained. Say for this triangular facet here, all of these regions will now have support structures. On all three edges and then everywhere in between. And these columns will extend to the top. And a simple way to calculate the support structure volume is as the sum of AI into HI going from 1 to n. N is the total number of down facing facets. AI is the projected area of the facet onto the horizontal slicing plane, and HI is the average support height evaluated from the corresponding facet to either the platform or the next intersecting facet. Why does it say next intersecting facet? So imagine that we are trying to print something like the letter E. Let us try to identify all the regions where supports will be needed. This bottom one by default, then this face here. But notice now that we are not extending the supports all the way to the build plate. They are limited to this height, which is the next facet. And what about the top structure here? Some of it will again be limited to the next facet. Some of it will go down to this bottom facet here. But again, none of it is reaching the build plate. So if we do our calculations with respect to the build plate always, we'll of course end up overestimating. And here again there is an example. On the right here, we have support which is projected all the way to the base. In the middle, there is a region where it is going till the next facet. But also, very interestingly, we have a region where despite having overhang, there is no support structure. And the reason for this is that even though the facet normal is pointing downwards, it is still less than the critical angle. Why we need to be careful with support generation and say post removal of support during post processing is because now these supports are coming in contact with the part also. For instance, here it is coming in contact here. Say if you project these support structure, now they are coming in contact with the part surface. In this case also, so and also with the top surface by the way. Here it is coming in contact with at least three surfaces. And so, if these support structures are not removed properly, they will leave some artifacts or remnants on the finished part surface, and that will affect the final part finish or the part quality. Another example, which Professor Kapil has discussed in great detail, will not go over it. But very briefly, what we can say is that we can always intelligently guess as to which facets might require, um, say, support structures. We have the facet normal and the three components of the facet normal. The last one being the Z component. Here we see that it is negative, so it may require support structures. Similarly here, this one as well. This will of course require because minus one implies that the facet is pointing entirely downwards. Here the criteria is given as nz less than minus zero point 0.5. So we will not consider these two facets because the criteria is that they should be less than zero point 0.5. Equality is just the limiting case. The next topic is support generation from contours, and there are two ways to do it. First is the containment method, and second is the optimal method. In both cases, however, what we are doing is we have these slicing layers. In this case, this layer is a plane, and these slicing planes intersect the 3D object, and the intersection of, okay, I should write it the other way. The intersection of slicing layer in this case a plane, and 3D object is the contour. The first method is containment. The second is optimal. Let's talk about the optimal method because it by its name itself we know that it is the more optimum one. In the optimal method, we generate the contours by slicing the entire object for each slicing layer, and then we use these contours to generate the support structures. But how? So we have the slices for each of the layers, say n minus 1, n minus 2, n minus 3, and so on. And here we have the union of two successive layers. So this is the union of n and n minus 1. This is for n plus n minus 1 plus n minus 2, as in this plus the next one, and so on. And this is the extra layer or the extra region where the support structure will be needed. So when we superimpose the n and the n minus 1th contour, we see that this region will not be supported by the immediately previous layer. And so in this layer, this is where we must have support structures printed. We take their union with the n minus 2th layer. This is what we get. And again, we try to examine what is the region which is unsupported, which is again highlighted in red here. And we keep doing this from the top to the very bottom. And then we generate supports in each layer only in this highlighted region. Another illustrative example to show this. And here we'll discuss the concept of stale and fresh support. We see that for this region, it is printed at the very last, given our layer height thickness. But to support it, we have to deposit the supports from the very first layer. But it is used as the very end and not for, say, the immediate next layer or for in the next few layers. So this is the region of stale support. Whereas if you look at this adjacent region here, we must print support structures here to support this region. For the next layer, we already know that we must print support structures here and so on. So this is the region of fresh supports. And we have spoken before about what can be an optimal orientation. But what defines this optimum condition? What are the constraints? What is the objective function to be achieved? Some of the most popular models for obtaining the optimal orientation are given here. One is the cost minimization model, where you ensure that by orienting your object in a certain way, you are minimizing the cost. Say if you orient it in a way which minimizes or eliminates the need for supports, then you don't have to print those support structures. So you're saving on the raw feedstock, you're saving on the power and time consumed. You may also save on some expertise, which is required for deciding what is the type of support to be generated, and on post-processing, during which you will remove this support structure. So it can be a cost minimization model, or it can be a support minimization model where you simply want to eliminate or minimize the supports because, as we saw, it can affect the part finish, or it can increase the amount of time required for printing the part. Or you can have a multi-objective model where you have multiple objectives and you assign weights to each of these objectives depending on how important they are, and you ensure that some extent of each is achieved. So all of these were discussed in detail. and I'll just touch on the multi-objective model and some of the interesting objectives which I put forth. One can be to maximize the number of perpendicular surfaces because a perpendicular surface will not require any supports at all. We can maximize the number of up-facing horizontal surfaces because again these will not require supports, or we can maximize the number of holes with their axes in the build direction. So say suppose you have a very simple shape like a cube or a cuboid which also has a cylindrical cavity inside. If your build direction is along positive z, and you also orient it along positive z, then we notice that there is no need for any support structures inside this hole. It is self-supporting. But what if we tilt this orientation somewhat? So say now if for instance this is my tilted configuration, now I see that say in this 2D figure this plane is unsupported. In fact this entire lateral surface is unsupported and so we'll need to have support structures here. And you will later have to remove these supports. If it's not a through hole, it will also be just trapped inside and it will affect the part quality. It will require post processing and further machining to get rid of these structures and it will be a hassle. So it is always very intelligent to maximize the number of holes with their axis along the build direction. Similarly, we can maximize the number of curved cross sections drawn in the horizontal plane or the area of the base surface, or we can minimize the number of sloped surfaces or the number of trapped items. Now let us quickly move on to the second lecture for this week, which dealt with slicing methods. And in this lecture, the topics that were stressed upon were the classification of slicing methods, such as whether they are direct or indirect, whether they are uniform or adaptive in nature, and whether they use horizontal layers or conformal layers for slicing. Then we discussed the uniform slicing of STL files in great detail because in most commercial applications, it is the process which is most commonly used, and that can be done through contour determination and contour organization. Slicing, as we discussed, is the say intersection of these slicing layers with the object, whether the actual 3D object or its approximation in the form of an STL file. And this slicing actually tells us what is the uh, part to be deposited in each layer, what is the height, what is the tool path that we have to take, and so on. Now, this slicing step itself can either be a direct slicing, that is, it is a slicing of a part obtained in a suitable format from any CAD format without the need for any intermediary format. What is an intermediate format? The STL approximation. It is generally stored in the form of analytical curves and mathematical definitions. And since the exact model is used for slicing, all the part features will be accurately reproduced. Here we have the example of a sphere, which in 2D appears like a circle. And if we slice it directly from the exact 3D representation, Then in each contour, what I will obtain is an exact circle. Say this is the n minus 1, n minus 2, 3, 4, and this is the n minus fifth layer. And this is the contour that we're observing in this n minus fifth layer, and what we see is that it is a perfect circle. However, this would not be the case in indirect slicing, where we have converted this 3D sphere into an intermediate format, such as STL, which approximates the circle with the use of triangles to form a geometry such as this polygon shown here. In this case, when we look at any random layer of slicing, we see that now the contour is not a perfect circle, rather it has these vertices and it is made up of straight line segments. However, irrespective of this approximation error, the index slicing method is the one which is most commonly used because it is simple and it is independent from specific CAD modeling methods. The second classification is based on the layer thickness, that is to say whether there is any variation in layer thickness along the build height, or whether if we simply fix our layer thickness uh, once and then use it throughout the build. We have an example here of an arch, of a feature with say something resembling an arch or a curved region, and if we slice it uniformly, that is the height of each layer is the same, we have a predetermined number of layers, and for the straight segments it works rather well. But for these regions which have curves, we see that there are large errors and we are under depositing, and this curved feature is lost. However, if we use adaptive slicing, where for regions with curvature we are working with very fine layer thicknesses, whereas for straight regions the layer thickness is far larger, then can retain these curved features as well. Of course, this leads to a larger number of layers and may lead to increased build times, but then your part accuracy is preserved. And it might be limited, however, by uh, say the technology you have. Typically, if the Z motion can be independently controlled, but you might still have a minimum layer thickness which you can deposit, and thus, irrespective of the height that you change, uh, say by lifting your deposition head or by bringing your table down, the minimum height which you can deposit with your given feedstock and given process parameters for a material, it may still be larger and we might still miss out on accuracy. Now, another type of classification can be based on what type of layer you are choosing to work with, because a layer can be horizontal or it can be conformal. The most common case that we typically encounter is, of course, of horizontal or planar slicing, which uses planes or flat surfaces to slide the object and deposit each layer on a planar pre-built surface, such as this flat substrate shown here, using 2.5 degrees of freedom. What is this 2.5 degrees? So 1 degree of freedom is along the x direction, one is along the y direction. However, the third degree of freedom along the z direction is not continuous. That is, we move the deposition head up or the build table down intermittently, and thus it is only counted as a zero point 0.5 degree of freedom instead of a complete DOF. So 2.5 degrees. The non-planar slicing or conformal slicing is again a biomimetic concept borrowed from nature. And in the example of the cabbage and onion shown here, we can see how starting from some seed or some core substrate, we can just build around it in layers and end up with the final geometry. So here we have a small spherical substrate around which these layers are deposited uniformly, and we end up with such a conformal sliced object. Another example can be a case where you want to deposit, say, a hemisphere, and so a hollow hemisphere, for example. And there we can start by having this hemispherical core, whether itself hollow or solid, and then we can have the layers deposited on top of it. And at the end of deposition, we can say remove the core, or the core can be embedded, and we can end up with a hemispherical part, which will be very difficult to print otherwise. Another classification for slicing is based on the approach used, whether it is a top to bottom approach, or a bottom to top approach, or one with negative tolerance or positive tolerance. Let us examine all of these one by one. So this one here is the top to bottom approach, in which we have sliced our object using these planar layers, and then we simply project the intersection of the slicing plane and the object, that is the contour, down. So this is the projection for the first layer. This is the projection for the second layer, which is the intersection of this cutting plane with the solid, and so on, until we come to this equator. Now what we see is that when we are projecting the contour downwards, now we are over depositing. Similar is the case as we continue to go below. So we have regions of under deposition, where there should have been material but there was not, and over deposition, where material was not supposed to be deposited but it was still deposited and we would need to be removed later. The bottom to top approach is just the converse of this, or the reverse of this. Again, we have sliced our object using these horizontal layers, and now starting from the bottom we are simply projecting the contours up. So for the first contour, this is the projection, the second contour, and so on. Again, after reaching the equator, we continue to project like this from the bottom towards the top, and now we have regions of over deposition. And once again, we have both the problems, that of over deposition and under deposition. The third is the case of negative tolerance, where we are being conservative and we are always depositing within the actual part geometry or the approximated geometry. So here we have under deposition everywhere and there is no instance of over deposition. This might be the case where, say, you do not have access to a post-processing facility for removing the extra material, or you are trying to be conservative uh, within the actual part geometry. And its opposite will be the case of positive tolerance, where you're always depositing a little extra material, because here maintaining the geometric accuracy is more important, and you have access to some post-processing facility using which you can get rid of all of this extra material. Which strategy you use and go with will of course depend on your specific case. Again, as we discussed, we use indirect slicing and we use indirect slicing of approximated or representative geometries, that is the STL files. In STL files, the surfaces are represented or tessellated with triangles, and thus the slicing of or the intersection of any slicing plane with such a triangle will occur at a few points, such as the example shown here, where it is occurring along these 2 points. The flowchart for implementing such an indirect slicing procedure is given here. Assuming that we are working with uniform slicing, which we typically do, we define the layer thickness T at the start of the process, and we also find the minimum Z coordinate and the maximum Z coordinate. So here this north pole is the maximum Z and the south pole is the minimum Z coordinate. And then what we do is we uh, say distribute this height difference Z max minus Z min into many layers, each of height D. So starting from the bottom, we will move up by a height equal to D to end up with the next layer and continue this till we reach Z max. Once this layering is done, uh, we'll work out the intersection points and then we'll have triangle sorting and grouping, triangle plane intersections and sorting the edges of the polygons. Then the contours will be organized and some offsetting procedure can be done depending on your requirement. Whenever such an indirect slicing is done, we should record the points of at which this intersection occurs. And depending on the exact case, say if the intersection is happening at 2 points of the triangle, we need to record both the points. If it is happening at an intersection point and at one vertex, we should record the intersection point and the vertex. In this case, where it is happening only at one of the vertices, we have to do nothing because the information on the vertex is already available. Here, where the intersection is occurring along an edge of the triangle, we should recall both the vertices and similar cases. We already saw the specific case when the build direction is aligned with the positive z direction and how to obtain the point of intersection in such a case. So here, the point of intersection can be obtained by the process shown here. This is the parameter t, which will equal this equation. And by finding the value of the parameter t, because we know the height of the intersecting plane, we can back substitute and find the other vertices of the points of intersection. We'll also do examples, numerical examples, to further illustrate this algorithm. And now that we have the points of intersection, we want to edge sort them to have a sense of how the points are connected or how the contour is constructed by the intersection of the object and the plane. And we also have a small example here which can illustrate this. I'm just checking how much content is left and we can take a break accordingly. So here we have an example where we are asked to sort the edges of the polygon. And we are already told that there are these points which were found to be the points of intersection and they are connected by these edges. So we construct this matrix. I'm just noting the general notation. So x1 of edge 1, y1 of edge 1 and x2 of edge 1 and y2 of edge 1. So I'm just encircling the edge number for easier identification. And we'll have to number the edges. and see how they connect. So starting with anyone, and we're starting with edge 1, we have x1 of point 1 is 1, and y1 is 1, x2 is 1, and y2 is 2. Now we have to try to match this second point, that is point 2 given by x2 and y2, with the one of the points of any of the other edges. We first look at the first edges, or first point, points 1 of each of these edges, and check whether 1 comma 2 is available. It is not. Then we look at the second point of each of these edges. Here we see that the point 1 comma 2, so this was edge 1. Now we see that the point 1 comma 2 is available with edge 3. So in this connectivity matrix, edge 3 will come next, and we write the point which it links up with, 1 comma 2, then the other point 2 comma 3. Again we are looking for point 2 comma 3, and we see that it is available here. So this is edge 2, 2 comma 3, and its other point 5 comma 4. Now we look for 5 comma 4 and find it here. So finally we have edge 4, 5 comma 4, and 1 comma 1. So what this means in essence is that once we have all of these points of intersection, the way they will link up to form the contour is that first we will have edge 1, P1, P2, then we will have edge 2, with, say this is of 1, and here we will have, oh sorry, edge 3 as per our matrix, and P2 of edge 3, P1 of edge 3, then we'll have edge 2, P1 of edge 2, and P2 of edge 2, and finally we'll have edge 4, P1 of edge 4, and P2 of edge 4. And to ensure that it forms a closed loop, we see that the last x1, xy, and the first xy points are the same. We also saw this in the definition of a valid solid. Now that the contours are sorted, we must also organize them. And organization basically means that we have to identify which are the contours within which material will be deposited, or if there are any empty contours, how these contours are linked to each other. And for this, a relationship matrix has been defined here. So this was also solved, and the solution is given by Professor Kapil, yet he will do it just to practice the algorithm. The relationship matrix has been defined here as follows: that if you are examining two contours, contour I and contour J, if contour I contains contour J, we will assign a value of +1. If contour I is contained within contour J, we'll give a value of -1. If they are separate and unrelated, we'll give them a value of 0, such as contour 1 and contour 8 here are totally separated. And if I and j are the same, we'll assign it a value of +2. In this matrix given here, I is going along down the first column, whereas j uh, is first row here. The first is I equal to 1 and j equal to 1, which will be +2. In fact, all of the diagonal elements will be +2 because here we have I and j equal. So let us just fill that first. Now for I equal to 1 and j equal to 2, we see that j is contour I contains contour j. So this is +1. 3 is also contained in 1. 4 is also contained in 1. 5 is contained in 1. 6 is contained in 1. 7 is also contained in 1. 8 is totally separate, and 9 is also separate. Now I equal to 2. 2 does not contain contour 1, however, it is contained within contour 1. So this value is minus 1. 2 and 2 are same. Contour 2 contains contour 3, so again plus 1. Contains contour 4, 5, and 6. It also contains contour 7, however, 8 and 9 are unrelated. Contour 3 is contained in contour 1 and is contained in contour 2. It contains contour 4, 5, and 6. However, it is separate from 7, 8, and 9. Contour 4 is contained within contour 1, 2, and 3. However, it is separate from 5, 6, 7, 8, and 9. Contour 5 is contained within contour 1, contour 2, contour 3. It is separate from contour 4. It contains contour 6, separate from 7, 8, and 9. Contour 6 is contained within 1, 2, and 3. It is separate from 4. It is also contained within 5, separate from 7, 8, and 9. Contour 7 is contained within 1 and 2, but it is separate from 3, 4, 5, and 6, as well as 8 and 9. Contour 8 is separate from 1, 2, 3, 4, 5, 6, and 7, but it contains 9. And contour 9 is separate from 1, 2, 3, 4, 5, 6, and 7. However, it is contained within contour 8. And after filling this matrix, what we find is that it is a skew symmetric matrix, as in the transpose is equal to minus 1 times the original matrix. Additionally, what we can also find out is which of these are exterior contours, as in an exterior contour marks the exterior boundary and it will have material within it, or whether it's an interior contour which will be hollow from the inside. And if you are looking at any contour I, if the number of times minus 1 occur in this relationship matrix is odd, then it is an interior contour, and if it is even, then it is an exterior contour, which is also illustrated here by the color red. So wherever the areas are filled with red color, those are exterior contours because they contain material, and all the hollow contours are filled with white color. And we can also form this, say, hierarchy matrix where we start by assuming some universal set 0, which contains all of these contours, which is the first level. 0 contains the contours 1 and 8. 8 contains only 9, so this is complete. Now 1 contains 2. 2 contains 3 and 7. 3 contains 4 and 5, and 5 contains 6. And so we have the relationship tree. Another example which you can practice on is given here. And some other features of adaptive slicing and why it may be used. So one of the case is to preserve the peak feature, as we're talking about peak features and curvatures. If we work with uniform slices, they need not always align with the feature of the material, even if it is not a curved feature, and they will be lost. However, by the use of adaptive slicing, these peak features can be preserved, curvatures can be preserved, and the cusp height can be minimized. The cusp height, of course, being say the difference between the actual geometry and your approximated geometry. And that is it for the content covered in this week. We'll take a short break now, and when we return, we'll discuss some example questions which will help us in solving the assignments. So we'll meet in some time. Hello and welcome back. So let us now look at a few example problems. The first one says that few lines of a triangle from the code of the ASCII format of an STL file are given. The three vertices are defined, and we are asked that if the triangle is rotated 90-degree counterclockwise about x-axis, then 90-degree counterclockwise about y-axis, and finally 90-degree counterclockwise about z-axis, what are the new coordinates of the triangle? This is a straightforward question, and we already discussed the derivation during in the first hour. So let us directly apply the formulas. We know that the we have to find all the coordinates of the triangle. So say this is point 1, point 2, and point 3. We'll have to find say P1 new, P2 new, and P3 new, and this will simply be we are first rotating about the x-axis, then the y-axis, and then the z-axis. And similarly for the others. Here theta x is pi by 2, theta y and theta z are also pi by 2, and so the rotation matrices will look something like this. The general formula is that 100 cos theta x sin theta x minus sin theta x are 0 sin theta x cos theta x, but theta x is equal to pi by 2, so this will turn out to be 100 minus 1 and 0 1 0. Similarly, our theta y, the general formula is cos theta y 0 sin theta y 0 1 0 and minus sin theta y 0 cos theta y. If we plug in the value of theta y equals pi by 2, this will come out to be 0 0 1 0 1 0 minus 1 0 0. And similar will be the case for r theta z. I've also written the formulas here. R theta z will come out to be 0 minus 1 0 1 0 0 0 0 1. And if we do this operation for any one point, say P1, originally P1 is given as 2 1 0, then r theta x times P1 will equal 1 0 0 0 0 minus 1 0 1 0 times 2 1 0, and if we work this out, this will be 2 times 1 plus 1 times 0 plus 1, simply 2. 2 times 0 plus 1 times 0 minus 1 times 0 is 0, and 0 times everything is 0. Oh, sorry. 2 times 0 plus 1 times 1 plus 0 times 0 is 0. We next multiply this with our theta y. This will be 0 0 1 0 1 0 minus 1 0 0 times 2 0 1. This will come out to be 2 times 0 plus 0 times 0 plus 1 times 1 is 1. 2 times 0 plus 0 times 1 plus 0 times 1 is 0. And 2 times minus 1 plus 0 plus 0 is minus 2. And for the last step, we will do r theta z times r theta y r theta x times p, which will turn out to be 0 minus 1 0 1 0 0 0 0 1 times 1 0 minus 2, which will come out to be 0 times 1 plus minus 1 times 0 plus 0 times minus 2 is 0. 1 times 1 plus 0 times 0 plus 0 times minus 2 is 1. 1 times 0, 0 times 0, and 1 times minus 2 is minus 2. So this is P1 new. And we can similarly solve for the other points P1, P2, P3, and the answers are given here. This is P1 new, P2 new, and P3 new. The second question is asking us again, the vertices of a triangular facet are given. It undergoes certain rotations, 90-degree counterclockwise about x, 90-degree counterclockwise about y, and 90-degree counterclockwise about z. Then what will be the unit vector corresponding to the new facet normal? And this is really simple. We did something similar already. The funny thing is that the vertices are the same as given previously, so we already know what the new set of vertices looks like after undergoing this rotation. The new vertex, the new vertices are 0, 1, minus 2, 1, 3, minus 4, and minus 4, 2, 2. So we now have a triangle, and we are asked to find the new unit vector corresponding to this, which is similar to the first question that we solved today. So we have the 3 points.
Excuse me.
All we need to do is find, just a second. Hi, Ramana Murthy.
Yes.
Hi.
So, uh, so why don't we multiply all the rotation matrices first, and because those are common for all the matrices, so then we can multiply. No, that will reduce the time.
Typically, we do this operation for one vertex at a time. The reason for that, again, I think what you're trying to say is that we can also put all of these vertices in a matrix and then, have this matrix multiplication, whatever r theta x, r theta y, and r theta z. But will this come out to be, say, same as doing it point by point differently? Is not something I have tried out, but you can definitely check and let us know next week if it comes out. If that is indeed so, then as you said rightly, we can save on a lot of effort. Yes, but it is not something I have tried out, so I can't really say.
It should come no mathematically, because the order we have to only thing is pre-multiplication we have to do. R theta
Uh,
x should be multiplied by r
no,
theta
but
y.
what we have to preserve is that each of these columns are containing the points. Whether after the at the end of this multiplication operation, each of these columns will correspond to the new points or not. That is something we should check before we comment because matrix multiplications are not so easy to generalize. Of course, it may be so as you are suggesting, but I would request that you try out this exercise and then let us know.
Okay. And in case of uh, clockwise rotation,
Yes.
how it will be different from this?
Okay. So The cases that we have been discussing are for counterclockwise rotation because you know that typically, the positive sense of rotation is considered as counterclockwise. But
Yes.
even if it is a clockwise rotation, say in some plane, uh, XY plane. So now what we're saying is that say instead of some counterclockwise rotation theta, now you have a clockwise rotation. Now you will reach the same position. Okay, maybe I should make it at some other angle. Say we have been talking about counterclockwise rotations, but you can also reach this point by a counterclockwise rotation, say some alpha. But you know, counterclockwise rotation alpha is same as 2 pi minus theta. So in all the formula that we have for a counterclockwise rotation, you simply substitute instead of theta, you use 2 pi minus theta. That is the only distinction.
Shall we put minus theta?
Because of the properties of sine and cosine, it will work out to be the same as minus theta or 2 pi minus theta because the periodicity is 2 pi. So yeah, the end result will be equivalent. But the way to understand it mathematically is that it's a rotation of 2 pi minus theta in the counterclockwise direction.
Okay.
Yep, happy to help. Um,
Thank you.
the question we were dealing with, of course, is pretty similar to what we have done. So we'll not solve it in detail. Again, the only steps to be done are finding these any two vectors. In the previous case, we found AB and AC. Take the cross product divided by the magnitude of this cross product, and you will end up with the new unit vector. Unit normal vector. The third question, again, few lines of the code are given. In this case, instead of rotations, we have translations. So the triangle is translated +2 unit along x-axis, then +3 along y, and +4 along z. What will be the unit vector corresponding to the new facet normal? And this might sound like a lot of work, where we again find the positions of the new vertices, find few vectors linking those vertices, find the unit normals, and so on. But if we are careful, we'll find that the present question deals with translation, and we'll assume that this is pure translation, so there is no rotation component at all. And what we know is that pure translation does not change the unit normal, and so we need not find it afresh. The unit normal is something we have already calculated in one of the previous questions. Again, we have some code, and here we are told that in a certain process, the triangles of the STL file with facet normals with an angle greater than 120 degrees from the build direction will require a support structure. And we are asked to find, given this line of code, whether the given triangle requires a support structure if the build direction is positive z. Now we would already have found the unit normal for this in a previous question, and I'm just writing that value here. Say this unit normal vector is 10I hat plus 4j hat plus 9k hat by under root of 100 plus 16 plus 81 197. This is a unit normal vector for the facet, and we need to check whether it will require a support mechanism given that the critical angle is 120 degrees from the build direction. We have the components of the normal vector, so we can find its angle of inclination. Um, the angle theta, so if theta is the angle of inclination of the facet unit normal with the build direction, then we can calculate it very easily using dot products. The dot product of n with the build direction, which is represented by k hat, will equal norm of n times norm of k times cosine of the angle contained between them. Now let us work this out. Then I hat plus 4j hat plus 9k hat by under root 197 times k hat equals, since it's a unit normal vector, its magnitude is 1. K hat is also a unit normal vector with magnitude 1. Only quantity remaining on the right hand side is cos theta, which would imply that I dot k is 0, j dot k is 0, only k dot k remains. 9 by under root of 197 equals cos theta, or theta equals arc cos or cos inverse of 9 by under root 197. And just allow me a moment to compute this. This comes out to be 0.8747 radians, of course, yeah, it's not degrees. And we can convert it to degrees, that will come out to be, so approximately 50.1169. Now the critical condition was that whatever angle this is should be less than the critical angle. In this case, the critical angle is given as 120 degrees. So here we have theta less than 120 degrees. So supports are not needed. In the given question, we are given an object of somewhat complex geometry, which has to be fabricated by an additive manufacturing process. Now, considering the optimal method of support generation from contours, and further we are told that the ratio of certain quantities, RC by RS, RC being this distance here, and RS being the radius of this sphere, if they are in a certain ratio, we are asked to find the volume of the stale and fresh support. Let us attempt this. Let us first try to just sketch and identify what will be the regions of stale and fresh supports. So say if we are building it on some substrate plate, the top region, as we can already see, is self-supported. It will not be needing supports. However, All of these regions would be requiring supports. Some of it will be stale, sorry for the asymmetric diagram, but you get the basic idea. And you have these regions of fresh support. And we are asked to find the ratio of volume of stale and fresh supports. So let us start by finding out the volume of fresh support. It can be approximated very easily because the region containing the fresh supports is something similar to, given that we do not know, given that we do not know by what height the model is subtended above the build plate, we'll just assume that in the limiting case, the sphere or the hemisphere just touches the build plate, such that immediately below it there is little to no support. However, we know that this is not true for a practical case, and there will be provided with a minimum height above which this will be suspended. So this is the region of supports. I have highlighted it with green, and this is just one section that we are looking at. Of course, if we rotate it, sweep it by 360 degrees and by 180 degrees about the z-axis, we'll get the volume. And let us also mark the dimensions. So this height is rs. Uh, half of this is also rs. And so what we're looking for is simply equal to the volume of the cylinder minus volume of the hemisphere contained within it. The volume of the cylinder, as you know, is pi r square h. So pi rs square, the height is also rs, minus the volume of the hemisphere, as you know, is, for a sphere it is 4 by 3 pi r cube, for a hemisphere 2/3 pi rs cube, which comes out to be pi rs cube minus 2/3, 1/3 pi rs cube. Now let us find the volume of the stale support. Again, let us just draw a simple schematic to understand what is the volume we are trying to find. And of course, inside we have the region which contains this sphere. Now we are trying to find out the region highlighted in red. This is RS and this here is RC. Now it's the difference in volume of the two cylinders. Volume of the outer cylinder minus volume of the inner cylinder. Again, pi RC square RS minus pi RS square RS, which is equal to pi RS times RC square minus RS square. Okay, no further simplification at this point, but we are asked to find the ratio of steel and fresh support. So volume of steel support over the volume of fresh support will equal pi RS RC square minus RS square by 1/3 pi RS cube. And let us try to simplify this. Pi will get cancelled. We have 3 RC square minus RS square by RS square, and this will be 3 times RC by RS square minus 1. The value of RC by RS is given to us as 4. This will be 3 times 4 square minus 1, 3 times 15, which is 45. And thus the volume of steel supports is 45 times that of fresh support for the given condition where RC by RS is 4. Here we are simply expected to answer by qualitative examination and not by actually solving. So we'll just do this last question, and, then we can break for today. It's already 8 p.m. So we are given 3 facet normals for 3 different facets of an STL file, and their components are listed here. So as we already know, this is the X component, say NX, the Y component NY, and the Z component NZ. For the first one, the values are 0.892, 0 and minus 0.452. For the second, it is 0.568, 0 and minus 0.823. And for the third, minus 0.947, 0 and 0.3212. Now, given that the build direction is along positive Z and the base is at Z equal to 0, which of the 3 facet normals will we recommend to examine for the requirement of support structures? As we already discussed, if the facet normal is pointing upwards, it will definitely not require any supports. If it however points downwards, supports may be needed. For a negative z component of the support of the facet normal, we know that the angle that it is subtending with the build direction is more than 90 degrees. So we will recommend for checking by the same criteria the second one as well. third one has a positive Z component, so we can be sure that it will definitely not require any support structures. And thus, just by qualitatively looking at and comparing the Z components, we can say which parts may or may not require support structures. The actual final verdict will, of course, be dependent on the critical angle for that process, machine, and material combination. And the last question is slightly longish, so we may take it up in the next week. But this was it for today. Thank you for tuning in. This was week two of the live sessions for the NPTEL course on fundamentals of additive manufacturing technology. I thank you for joining in and look forward to seeing you next week. Thank you.